Lewis structures show us the attachment of atoms to each other in molecules. However, they can be somewhat deceptive into tricking us into believing that what we draw on paper is actually the shape that a molecule has. Rather, molecules exist in three-dimensional space and not two-dimensional space, unlike a sheet of paper, and so the way a molecule comes together is important for us because it can have some pretty significant biological implications, for example, if you're designing a drug. Now, what we do is we take a Lewis structure and then we have to basically interpret it and apply what we know about molecular geometries. And molecules always seek to spread atoms as far away from each other as possible, and it follows a model known as valence shell electron pair repulsion theory, or VSPER theory. Basically says the best arrangement of a given number of electron domains is the one that minimizes the repulsive forces amongst them. That is, atoms try and separate as far away from each other as possible while still maintaining their chemical bonds. So let's talk about this idea of an electron domain. Electron domains are areas that surround a central atom which have electrons in it. And the number of domains is independent of the number of electrons in the domain, rather how many different geographical locations there are. Whether it's a single bond, a double, a triple bond, or a lone pair, each one of these would be a domain. Let's take a look in a little more depth here. So in this molecule AB3, we have one domain for the single bond. We have a second domain from a single bond. We have a third domain from the double bond. And we have a fourth domain on the lone pair. So we've got 4 domains in this molecule AB3. And again, it doesn't matter how many electrons are in each domain, it's the fact that there's some space, and in that space there are electrons present, whether it's 2 or 4 or 6, doesn't matter. It's the actual space itself that is what defines the electron domain. Now, molecules we use electron domains to determine electron domain geometries. And there's 3 electron domain geometries. That's not to say that there's 3 geometries, there's just 3 electron domain geometries. And we're going to go over those here in a second. So the 3 types of geometries are based off of having 2 electron domains, 3 electron domains, or 4 electron domains. And those are linear, trigonal planar, and tetrahedral. To figure out which electron domain you have, you simply count the number of domains around a central atom. So NH3 has 4 electron domains, which puts it under the tetrahedral electron domain geometry. However, NH3, ammonia, even though it has 4 electron domains, only 3 of them are occupied with bonds and 1 with a lone pair of electrons. So we have a molecular geometry as well. And a molecular geometry is a little more important than the electron domain geometry, in my opinion, because it actually tells you something about how the structure of the molecule is set up and what the dimensionality of the molecule is. To figure out the molecular geometry. The molecular geometry is really concerned with how the bonds between atoms are oriented and ignores the lone pair of electrons on a central atom. So for example, in our example of NH3 here, there are 4 domains, which puts it under the tetrahedral electron domain geometry. However, since of those 4 domains which are occupied with electrons, 3 of them only have bonds, we consider it to be a trigonal pyramidal geometry shape. So I'm going to briefly go over the different shapes here. We've got an electron domain geometry of 2, where both domains have bonds in them. We form a linear molecule, so CO2. And we call this linear because, well, everything lines up on a line. If we have 3 electron domains and all 3 of them are filled with bonds, such as boron trifluoride, we have a trigonal planar The trigonal planar geometry has bond angles of 120 degrees, and they all lie on the surface in which they are drawn on. So this is an example like linear, where what you draw on paper actually reflects the Lewis structure you've got as well. So we can't be fooled with the trigonal planar. However, if one of the bonding domains, if one of the electron domains has a lone pair on it, then we have a bent structure. We have two bonding domains, one non-bonding domain. What happens is the molecule gets bent a little bit, and so we have a bond angle between the outer atoms of approximately 118 or so. Bond angle deviation really isn't too significant from trigonal planar. So if you were to say the bond angle is 120 for both bent and trigonal planar, when you have three domains, that is fine. And I'm going to stress three domains because we'll see here in a second there's another bent geometry based off of four domains. So let's go ahead and take a look at those geometries. Four electron domain geometries fall under the category of tetrahedral. And what we've got is when we have all four of those domains with bonds in them, we have a tetrahedral structure. Bond angle is 109.5. If one of those domains is a non-bonding domain, that is, there's a lone pair on it, we form trigonal pyramidal. And if we have two non-bonding domains of our four, then we have a bent structure whose bond angle is also about 109.5. So you have to be careful with bent. Now, unlike the linear and the trigonal planar and the bent with 120 degree bond angle, tetrahedral is the first time where if you draw a Lewis structure and you look at the paper and you say, oh, well, all my bond angles look like what I've got drawn on the paper, you're going to be wrong because tetrahedral is a three-dimensional molecule geometry. It extends out the atoms as far away from each other as possible. And in a 360 degree sphere or spherical world we live in, the furthest these atoms can get from each other is 109.5 degrees.